the last thing we want to do is we want to relate our new knowledge of Newton's law of universal gravitation to some of our other previous equations. So the first thing that we want to do is we want to look at the relationship between this and F net equals ma. Now, one of the things that you can realize is that in both cases you have a force. So if you were to divide this side by m and divide this side by m, what you'd have left is an acceleration. Well, the same is true here. If you were to divide this side by m and this side by m, what you'd have left is an acceleration. So you can figure out the acceleration due to Earth by just saying g mass of Earth divided by the distance from the center of Earth to the surface. And that would allow you to calculate the acceleration due to gravity. The 9.8 number that we're so familiar with comes from the fact that whenever you take these numbers and you plug the variables for Earth in, it ends up being 9.8. So you should be able to relate Newton's law of universal gravitation to the idea of gravitational force or attraction. But you should also be able to relate it through Newton's second law to acceleration or any of the kinematics motion equations. This is any force. Any force could then be solved for any acceleration, and any acceleration could be plugged into the kinematics motion equations. Now, the other thing that you could use is what we talked about in a previous section in this unit. An object like the Earth goes around the Sun. We'll say this is the Sun and this is the Earth in an approximate circular orbit. Now, we said whenever something moves in a circle, it's because it has centripetal force. Well, the centripetal force, remember, we said is a description of the forces that make an object go in a circle, but there is no actual centripetal force. What we said is the centripetal force is something else, and we call it a centripetal force because it goes in a circle. Okay, so the reason why the Earth goes in a circle around the Sun is because of gravity. So there are situations in which we can say the gravitational force is equal to the centripetal force. So let's look at a couple of examples. All of these are mastery level questions because what they're trying to do is they're trying to relate it to the previous learning. It's trying to make connections for you. So there is some math intensity here. Now it says two asteroids, each with a mass of 1,000 kilograms, are initially separated by 1,000 meters. If the asteroids are initially at rest relative to each other, how long will it take for them to collide? Now, we're going to do a very, very basic calculation here. The actual answer is much more complicated that we'll talk about in a little bit. But for now, we're going to say that we have the mass 1 equals mass 2 equals 1,000. Both masses are 1,000. In addition to that, we know that the distance is 1,000 meters. Now, if the asteroids are initially at rest, so I know VI equals 0, how long will it take for them to collide? So I'm actually end up looking for a time. So whenever you're looking for a time, a lot of the times you need to use one of the kinematics motion equations. So we need to figure out how we can get a third variable. So if I were to make a guess at this point, the equation that I'm going to have to use is d equals VIT plus 1 half AT squared. Now the reason why I can guess this equation is because I have the distance. I have the initial velocity. I'm trying to solve for the time. And acceleration, remember, is the link between force and motion. So because of that, I'm pretty sure that's the equation that I'm going to have to use. The problem is I don't have acceleration. So what I'm going to need to do is I'm going to need to use Newton's law of universal gravitation to solve for the force. Once I have the force, I can say F equals ma, and then go from there. So the first thing that I'm going to need to do is I'm going to plug into the equation F equals g m1 m2 over d squared. When I plug in, I get 6.67 times 10 to the minus 11th times 1,000 squared, because they're the same, divided by 1,000 squared. Well, that makes it super easy. 1,000 squared divided by 1,000 squared cancels out, and my force is the same as this number. So once I have my force, I can now use the equation. I'm going to change colors just to say I'm changing equations. F equals ma. Or I can plug in 6.67 times 10 to the minus 11. Remember, that's the gravitational force that I just calculated. Equals the mass of these particular asteroids. Just pick one. 1,000. Okay? And then divide by a. Or excuse me, and then that's a. So you can quickly find the acceleration to be a pretty substantial number of 6.67 times 10 to the minus 11th. Now, or excuse me, 10 to the minus 14th. Now, once you've established this, it creates kind of a problem at this point because you've been talking about one particular, both asteroids. Whenever you look at the total distance is 1,000 meters. But only one asteroid, this asteroid right here, only has to travel 500 meters for it to meet. So the distance that I'm going to plug in here is not going to be 1,000, but is instead going to be 500. So I plug in 500 equals, and then this term zeroes out, plus 1/2. You'd have an extremely small acceleration, and then you'd have t squared. Okay, whenever you do this and you divide everything out, it ends up being an extremely large number. Okay, we can take 500, we can multiply it by 2, and then divide it by our 6.67 E14. And whenever we do that, we end up with an exceptionally large number of something like, oh, we forgot to take the square root, that's why. Okay, you end up with something like 1.1 or 1.2 times 10 to the 8th seconds. But the problem with that is the attraction will actually happen much faster. This is our answer. This is what we're going to stick with. But the reason this is an exceptionally complicated problem that you wouldn't see for another couple of years would be the fact that we made the assumption that the gravitational force between these two asteroids was going to be a constant the entire time. But in reality, what's going to happen is the asteroid's going to move to here and here. Now, how is the gravitational force different than here? Well, if you look, the distance decreased. Well, as the distance decreases, remember the force goes up. So you're going to have a continually changing force. Now, that is beyond the scope of this class. So I just want to kind of present the idea to you and say it's a little bit more complicated than you would think relating it to motion. Now, it says the Earth's orbit around the Sun can approximate a circular path. The Sun has that, is separated by that. So now, what we can say is, what is the velocity of the Sun? So I'm trying to relate the attraction between the Earth and the Sun to speed. And not only speed, but speed in a circular path. So in this particular situation, I'm going to say Fg equals Fc. Whenever I do that, I can say, okay, G m1 m2 over d squared is equal to mvt squared over d. Now remember, whenever you're calculating the centripetal force, this mass right here represents the object that's in the outer part. That cancels out, and that also cancels out the mass of Earth. The mass of Earth is irrelevant towards its speed, so it makes no difference. This distance right here, you have a distance and a distance squared. So you can actually eliminate this term and cancel out the square. So what you're left with now is Vt equals the square root, because remember it was Vt squared, of G m1 over d. This is how you can calculate what's called the escape velocity for different planets as well. How much velocity you have to leave the gravitational pull of Earth. Think of it like a space shuttle. So we're talking about rocket science here. But you can also use it to calculate the velocity, in this case, of the Earth moving around the Sun. So I'd plug in 6.67 times 10 to the minus 11th times the mass of the Sun divided by the distance between them, which is 1.5 times 10 to the 11th, and I take the square root. Whenever you do that, you end up with a velocity of approximately 29,750 meters per second. The last example we have says, what would the acceleration due to gravity on Earth be if the distance from the center of the Earth was increased by 10,000 kilometers? The mass of the Earth is 5.98 times 10 to the 24th. Now, if you notice, I'm not originally given the distance to begin with. So, let's look at the equation. Fg equals G m1 m2 over d squared. Okay, we know that the acceleration due to gravity, when we divide mass out, we get an acceleration is equal to G m1 over d squared. That's what we talked about before. We divided both sides by mass, we get an acceleration, and this is what we're left with. We know that the acceleration due to gravity is 9.8. We know the universal gravitational constant is 6.67 times 10 to the minus 11th. We also know the mass of the Earth is 5.98 times 10 to the 24th. So we can divide by the distance, and we don't know the distance, so since we don't know the distance, we'll have to calculate it. We multiply both sides by d squared, we divide both sides by 9.8, we take the square root, and when we do that, we actually get the distance, or the radius from the center of the Earth to the surface, is about 6,379,000 meters. It's pretty large. But now, we're increasing the distance by 10,000 kilometers. So what that means is I'm going to do this exact same calculation here. 6.67 times 10 to the minus 11th, 5.98 times 10 to the 24th. But instead of dividing it by this squared, we have to add the additional 10 million kilometers. So you get this squared. And we can calculate the acceleration. When you do that, the acceleration gets to be much, much lower. You get the acceleration of about 1.48 meters per second squared. This right here approximates the acceleration on the moon. The moon has an acceleration due to gravity of roughly 1.6. So in order for us to have the same gravitational pull as the moon, you'd actually have to increase the distance or go about 10,000 kilometers above the surface of the Earth.